sixth lecture of our introduction to modular forms. So last time we proved the convergence of Eisenstein series, and then we've seen that to each modular form there is a Q series expansion attached with it. So let's say if F is a modular form of weight K, then we've seen that we can write the function f of z as f tilde of q, and which is a series a n q to the n, where n runs from 0 to infinity. And the coefficients a n are called the Fourier coefficients. Right? And also last time we derived the q expansion of Eisenstein series. For example, let's say Ek is the normalized Eisenstein series of weight k. So then the Q expansion of Ek is 1 minus 2k over bk sum over sigma sub k minus 1 of n q to the n, right? Where n runs from 1 to infinity. And bk is the Bernoulli number. And this sigma k minus 1 function, this function is really important in number theory. So this is defined as this: sum over d to the k minus 1, where d runs over the set of divisors of n. Okay. All right. So now let's see some examples. For instance, we can write E4 as this Q expansion like this: 1 plus 240Q plus 2160Q squared plus 6720Q cubed, and so on and so forth. And yeah, E6 is 1 minus 504Q minus, well, yeah, 122,976 Q cubed. Okay, so let us write E8. So there's a point for writing all these Q expansions of modular forms of Eisenstein series. So E8 is 1 plus 480Q plus 61920Q squared plus 1050,240Q cubed. Okay. Do you see a relation between E4 and E8? Okay, that's a very nice observation. So 480 is twice 240. And what about this one, 61920? What about this one? No. So I guess it's better if you have a calculator. So it's it's 240 square plus something. 240 square plus 2 times 2160. Can you guess something from this? The coefficient of Q is twice the coefficient of Q in E4. And the coefficient of Q square in E8 is the square of the coefficient of Q time plus twice the coefficient of Q squared in E4. The third bit, meaning this one? Okay, what's your guess? That is?
I'm guessing is 240 square plus 2160 cube.
So E8, the whole thing should be some square root of it.
Yeah, exactly. So E8 is the square of E4. Okay. So yeah. So we are like guessing this by the looks of the first few coefficients, right? So of course we need to prove it. So yeah, probably we have a guess that probably E8 is going to be the square of E4 because the first few coefficients they match up, right? Okay. And should I write E10? Okay, let's just write it. E10 is 1 minus 264q minus 135432q squared minus 5196576 q cubed. Okay. And yeah. So again, any guesses by the looks of E4 and E6?
164 or 264.
264. So exactly. So E10 is E4 times E6. So again, this is a guess. So of course we have to prove it. And turns out our guesses are true, and the key to proving these identities is the finite dimensionality of modular forms. So let M sub k be the set of all modular forms of weight k. Then M sub k is a vector space. It's a vector space, meaning we can take any two modular forms and we can add them and get another modular form of same weight. So if f and g are modular forms of weight k, then so is f plus g. And I think, well, I have to mention it that it's vector space over the field of complex numbers. And if I take a modular form of weight k and take any complex number, let's say c, then the scalar multiple cf is also a modular form of weight k. Okay. So yeah, and
Adding is defined by modulus.
right, exactly. So f plus g is supposed to be a function. So this function takes an input in the upper half plane and gives us the output f of z plus g of z. And yeah, and the key of today's lecture is the finite dimensionality of these vector spaces, and we'll prove that these vector spaces are all finite dimensional. And there's a very cool formula for the dimensions. So let me just write it. So dimension of mk. Of course, we know that if k is odd, then this dimension is 0, right? Because we've seen that the only modular forms of odd weight is the constant function 0. So this is floor of k over 12 if k is 2 mod 12, and this is floor of k over 12 plus 1 if k is not 2 mod 12. And this is true for k being positive. So we'll prove it. And those of you are familiar with solving Diophantine equations, so you can guess that this quantity is right here. So this is exactly equal to the number of solutions of a very specific Diophantine equation. That is 4x plus 6y is 12. Sorry, is k. I'm sorry. Okay. So for even k, for even positive k, there are exactly these many solutions to this Diophantine equation. Okay, and we'll see how this helps us. Okay. So, firstly, we have mentioned that while defining Eisenstein series, that the modular forms of negative weight do not exist. But we haven't proved that. So, first of all, we need to prove that. Okay. Let's get started with that theorem that says that if k is negative, then the only modular form of weight k is the constant function 0. Okay, so we are going to prove that now. Okay, suppose f is a modular form of weight k, then we have seen that there is a q series expansion of f. Let's say its q expansion is sum of an qn. So it suffices for us to show that all these Fourier coefficients an are 0. So we are going to show that all the ans are 0. So this is what we are going to prove. Okay. Yeah. And since f is a modular form, by the definition of modular forms, we have that f of az plus b over cz plus d is equal to cz plus d to the power k f of z. And this is true for all a, b, c, d in SL2Z. And also, we know that the imaginary part of az plus b over cz plus d is equal to the imaginary part of z over cz plus d mod square. Okay. Then let's consider the following quantity, that is f of az plus b over cz plus d, the modulus of it, times the imaginary part of az plus b over cz plus d to the power k over 2. Okay, then what is this? This is cz plus d to the power k f of z, and from here we have the imaginary part of z to the power k over 2 divided by cz plus d mod to the power k, right? So this gets cancelled out.
So CZ plus D, how it comes from the imaginary of KZ plus CZ plus D.
Yeah. So this comes from here, from the definition of modular forms. And if we expand this part, we get 1 over cz plus d to the, yeah. So therefore, we get that the function f of z, modulus of f of z, and times imaginary part of z to the power k over 2. It's an SL2z invariant function. Okay. Yeah. So it's an SL2Z invariant function, and we have seen the fundamental domain of the action of SL2Z, right? The fundamental domain is also this function. The domain of this function is H. Domain is the upper half plane. Okay. So this is the upper half plane, and this is our fundamental domain, right? And yeah, and this fundamental domain is defined by all the z in the upper half plane such that the absolute value of z is greater than or equal to 1, and the real part of z is between negative half to positive half. And given any z on the upper half plane, there exists a number in this fundamental domain such that we can go from this point to this point via an action of SL2Z. Okay. All right. Okay. Therefore, we can conclude that any function that is SL2Z invariant has all its values achieved in this fundamental domain. So if let's say z is in the image of the function, let's call the function g. So this function is called g, and g is an SL2Z invariant function. So if z is in the image of g, then there exists some, let's say, z naught in the fundamental domain such that z is equal to g of z naught. Okay. Because of course, since z is in the image, so z is equal to g of, let's say, z1. And yeah,
So isn't because it's invariant?
yeah, it's invariant. Yeah. It's not quite a fixed point because, well, fixed point is defined as g of z equals z. So it's not a fixed point.
Under SL2Z.
Yeah. So this g function is SL2Z invariant. So yeah, so since z is in the image of g, then z is equal to g of z1 for some z1, and f is the fundamental domain. So there exists some complex number in this fundamental domain such that this z1 and this z0 they are related by a by, they're related by a matrix of SL2Z.
Right.
Right. So that's why, yeah. Okay. All right. And yeah. And also we know that since f is a modular form, as z goes to I infinity, this is bounded. So this was the third condition we required in the definition of modular forms.
So is Z, which we define as G of Z naught, where is Z located? Is it located within the so Z is the image of G, right?
Yeah. And
So does it have to be located in the upper half plane?
well, we define G as a real valued function, right? So
Oh, I see.
so G is so Z is a real number in this case.
Oh, I see. So it's modular. No. It's not modular.
All right. So yeah, the modulus of f of z is bounded as z goes to I infinity, and also the imaginary part of z raised to the power k over 2, this goes to 0. Like as z goes to I infinity. So okay, can someone tell me why this is true? So as z goes to I infinity, the imaginary part of z goes to infinity. Why does this approach 0?
Sorry, you mean mapping from Z or F?
Which one? So, so this was one of the conditions we required in the definition of modular forms.
That if Z goes to imaginary infinity, F of Z remains
Bounded, right?
And you're saying that implies.
No, this does not imply that. So I'm saying that as z goes to I infinity, this also happens, that the imaginary part of z raised to the power k over 2, it also happens.
Raised to the power K over 2.
So as z goes to I infinity, the imaginary part of z goes to infinity. But we chose k to be a negative number. So that's why this limit is 0. So therefore, limit z goes to I infinity f of z, imaginary part of z to the power k over 2, this is 0. Because one part is 0 and the other part is bounded. Okay. Therefore, there exists some b such that f of z, imaginary part of z raised to the power k over 2, this is smaller than or equal to 1 for all z with imaginary part of z bigger or equal to b. Okay.
Is this a maximum
No, it's just a definition of limit. Yeah. Okay. Now let us cut the fundamental domain in two parts. So this is until when imaginary part of z is smaller than or equal to b, and this is when the imaginary part of z is larger or equal to b. This region right here, this is a compact region. So our function g is obviously bounded here, since this region is compact. And also in this region, we have proved that, well, we have chosen b in such a way that in the upper region, our function g is bounded by 1. So therefore, g of z is bounded by some constant c. And this is for all z in the fundamental domain. And also, since g is a SL2z invariant function, we can safely write that for all z in the upper half plane. All right. Yeah. So let us now write our function f. Oh, so how is g defined? G is defined as f of, let's say z is x plus iy and y raised to the power k over 2. Okay. And yeah. So let's consider the q expansion of f. So f is the modular form. So we want to show that f must be 0, right? A n q n, and that is, and q is e to the power 2 pi I z. So 2 pi I n z. Okay. And since z is x plus iy, we can write it as a n e to the negative 2 pi ny e to the 2 pi I n x. Okay. So now what we are going to do is that we take f of x plus iy, we multiply it by e to the negative 2 pi I mx, and then we integrate from 0 to 1. Okay. Yeah, and also, yeah. So while doing this integration, we have to switch integration and sum once. So how is that justified? Because this sum right here, a n q to the n. Yeah, this is actually this is a stronger convergence. This is uniformly convergent as well, since it's a Taylor series of a holomorphic function. So it's also uniformly convergent. So we can switch sum and integration. So this is sum of a n e to the negative 2 pi ny integration 0 to 1 e to the 2 pi I m minus n x dx. Okay, so this is the delta function. So we get that this sum is nothing but am e to the negative 2 pi my. Okay. Okay, now what? Now, yeah. So let's take absolute value on both sides. So am is equal to e to the 2 pi my integration 0 to 1 f of x plus iy e to the negative 2 pi I mx dx. Okay. And yeah, and this is using triangle inequality. This is smaller than or equal to this f, and the absolute value of this part is 1, right? Where?
In the exponent, there's y for the first factor.
Oh, yeah, right. Yeah, thank you. Okay. And yeah. And also, we know that f is bounded by c times y to the negative k over 2. So this is bounded by e to the 2 pi my c times y to the negative k over 2. Right. And since like now we have like only constant 1 inside the integration, so yeah, right. All right. And this is true for all y greater than 0. Actually, strictly greater than 0, because y is our imaginary part, right? So, and we are working in the upper half plane, so the imaginary part is always positive. Yeah. So therefore, let's write it again. E to the 2 pi my c y to the negative k over. Now what we are going to do is that we are going to take the limit as y goes to 0. So this part becomes 1 and this part vanishes.
Is k negative?
Yeah. So therefore am is 0. And this is true for all m. Therefore our modular from f must be 0, and hence the modular from negative weight are only the constant function.
So I mean, I know it's a line number, but y can never actually be 0.
No. So that's why I've written y approaches 0 plus. So it's only approaching to 0 from one side. Okay, so before we prove the finite dimensionality of other positive dimensions, other positive weights, so we need to prove another lemma. So let's state it. So that lemma states that there exists a modular from which we call delta of weight 12 such that it vanishes nowhere in the upper half plane, and also it has a simple zero in the point of infinity. So what this tells us is that means that so it's a function on the upper half plane, right? So if we take any point in the upper half plane to be an input, it never becomes zero. Okay, what do we mean by a simple zero at I infinity? We mean that the q expansion of delta is q plus b2 q square plus. So there's a constant term in front. So like ideal, I should have written b1 q, but we can always like scale that up.
And then divide the q with 1 with q, that becomes a simple.
Sorry?
I mean, it has a simple pole
Mhm.
at infinity. Simple
Right.
0.
Simple zero at infinity.
Zero.
Yeah. Okay, like while proving that like all modular forms have a q expansion, what did we do? We like given a modular form which is a function on the upper half plane, we define another function which is on the unit disk. Well, initially we did it for the punctured disk, then we've shown that this function f tilde is also holomorphic at the center. So yeah, we can like remove this prime. Okay. And so what does f tilde of 0 represent? So f0 is the center of the disk, right? And if you remember, so we define f tilde of q to be f of z, where q is e to the 2 pi I z, right? So if q is 0, that means the imaginary part of z is infinity, right? So the point 0, so f tilde of 0 actually represents f of I infinity. Okay, and when I write that like delta has a simple zero at I infinity, I mean that the Q expansion of delta has a simple zero in the origin. Okay, so since it's a simple zero, so the order of the zero is 1, right? So we can factor, like, well, Q minus 0 to the power 1. We can factor that up. So that's what it means. Well, yeah, as I said, I probably should have written B1Q plus B2Q squared, but we can always scale that out. So it's just Q plus B2Q squared. So, okay, but why is this lemma important? This lemma is important because 12 is the minimum way for which this is true. So let me say it again. So why 12 is the minimum? Because if, let's say, f is a modular form of weight k, and if 3 does not divide k, then f of omega is 0, where omega is the cubic root of infinity. So sorry, cubic root of unity. So yeah, if 3 does not divide k, then f of the cubic root of unity is 0. And if 4 does not divide k, then f of I is 0. Yeah, well, you can prove these two like very easily. Let's say, suppose 3 does not divide k, okay, and suppose omega is a cubic root of unity. Then what is omega plus I? So omega plus 1. Omega plus 1 is negative omega squared, right? Yeah. And from the definition of modular forms, we know that f of omega plus 1 is equal to f of omega. Since omega plus 1 is negative omega squared, so this is true. Also, we know that f of negative 1 over omega is equal to what? No. F of negative 1 over z is equal to z to the kf of z. So this is omega to the power k, which is not 1 since 3 does not divide k, times f of omega, right? And negative 1 to the, negative 1 over omega. So that is equal to f of negative omega squared, right? And that is equal to f of omega. So f of omega is equal to a number that is not 1 times f of omega. So this is true only when f of omega is 0. Okay. And similarly, you can do it for 4 as well. And okay, so there's a nice conjecture from this, that is, if n does not divide k, then f of nth root of unity is 0. But turns out this conjecture is not true. I don't really know whose conjecture it was. But yeah, so you can also like give a counter example for when let's say n is 8 or 10. So for n equals 8 or 10, there are counter examples. So this is in general not true, but these two are true. So therefore, if we want to have a modular form that vanishes nowhere, the weight must be divisible by 12, right? And now we're going to prove that, well, for weight 12, such a modular form exists. Okay, proof. So for this proof, we are going to use a variant of Poisson summation formula. So last time we've seen that, in fact, we've proved that the Poisson summation formula, that is this, where n runs over the set of integers. And f hat is the Fourier transform of f. Okay. But now we are going to use another identity, that is sum of -1 to the n minus 1 over 2 f of n. This is equal to, this runs over n in z such that n is odd. So this is equal to I over 2 sum over -1 over -1 to the power n minus 1 by 2 f hat of n by 4. And also here as well, this is n in z and n odd. I'm not going to prove this, but I'm going to give you enough hints to prove it yourself. So for this, what we're going to do is that, let's say we are going to define a function fab of x, which is defined as f of ax plus b. Okay. Then we're going to take the Fourier transform of fab. So the Fourier transform of fab is given by 1 over a e to the 2 pi I b over a. So fab of y, the Fourier transform of f evaluated y over n. So you can prove this very easily. Then this sum on the left hand side is sum of f of 4n plus 1 minus sum of f of 4n minus 1. And in these two sums, n runs over set. Okay. Then you can use the Poisson summation formula on these two sums. Yeah, n odd.
In the sum n is odd. Last time.
Here, no, here n is any integer. Well, in the odd number, so we have two options. The odd number is either 1 mod 4 or -1 mod 4. So I just wrote those two cases separately. Yeah. And then you can use the Poisson summation formula on these two sums and get this one. Okay, so we are going to use this formula on a function that is defined as f of x is x e to the negative pi ax squared. Okay, again, in order to use the Poisson summation formula, we need to verify that the function and its Fourier transform both are absolutely integrable. Because otherwise, we cannot switch sum and integral, which we did in the proof of Poisson summation formula. Okay, and I'm not going to evaluate the Fourier transform of this function, but yeah, that's left as an exercise. So how do we do that exercise? The Fourier transform of x e to the negative pi x squared, that is, I think, iy e to the negative pi y squared. Okay. So, yeah. So what is the Fourier transform of this e to the negative pi ax squared? This is just if this function is f of x, so this function is f of square root of ax, right? So if we use, where is it? Yeah. If we use this formula, you get that the Fourier transform of this function is given by wait, is there a negative sign in this Fourier transform? Let me look it up real quick. So, yeah, there's a negative here. Sorry. Okay, so if we use this formula, we get that negative iy over a e to the negative pi y square over a. Okay. So what will be the Fourier transform of f? Sorry, by f I mean this function. So if this is g, this is g of square root of ax. Okay, so what is the Fourier transform of f then? It's just this divided by square root of a, that is negative iy a to the 3 over 2 e to the negative pi y square over a.
So the f is the first function with the x,
Yeah, so
the Gaussian times x,
yeah.
and you're saying what is the Fourier transform of that?
So like the Fourier transform of G is left as an exercise for everyone. So using that,
So it says the same thing as g to the 5.
yeah. Okay, so and let's write f of what f of x is. F of x is x e to the negative pi a x squared. Okay, now my claim is that both f and its Fourier transform both are absolutely integrable. Can you see why that should be true? So
Isn't that part of the derivative conditions?
yeah. So we are using the Poisson summation formula. So we need to verify that like both of them are absolutely integrable. So in fact, so you can see that this is like both of the functions are nothing but like the Gaussian multiplied with x and y for the Fourier transform. So a more general result is true, that is Gaussian times any polynomial is absolutely integrable. Okay, so absolute integrability of these two functions are verified. Now we are going to use the second variant of Poisson summation formula that we did not prove, this one. So we are going to use this formula for f and f hat. So what do we get? On the left hand side we have sum over all the odd n, that is negative 1 to the n minus 1 by 2 times f of n. What is f of n? F of n is n e to the minus pi a n squared. Okay, and that is equal to I over 2, again sum over all the odd numbers, odd n, negative 1 to the power n minus 1 over 2, yeah, times f of n over 4, right? F of n over, sorry, f hat of n over 4, I'm sorry. So that is negative iy divided by a to the power 3 by 2 times e to the minus pi y over 4 whole square, that is y squared over 16. Okay. I hope I didn't make any mistake. Yeah. Now this is equal to, so we can multiply I n minus I to get 1, and we can take the, yeah, this should be y over 4. Yeah. So this is 1 over 8 times a to the 3 over 2, again sum over all the odd n, negative 1 to the power n minus 1 over 2. Why did I write y? It should be n, because in the right hand side the sum end is f hat of n over 4. Yeah, all these y's are n's. N e to the minus pi n square over 16. Yeah, now it makes sense. Yeah, now what we're going to do is that we replace a by a over 4. Okay, so of course we have to replace it on the both sides of the equation. So the left hand side becomes sum over all the odd n negative 1 to the n minus 1 by 2 n e to the negative pi a n square over 4. Right, and in the right hand side we have 1 over 8 times a to the 3 over 2. So 4 cube is 64, 64 square root is 8, so the 8 gets cancelled out. We have 1 over a to the power 3 by 2, and the sum over odd n, negative 1 to the power n minus 1 over 2, n e to the negative pi n square over 4a. Yeah, I hope this is correct. Okay, and we can make a very cool observation, that is the n terms and the negative n terms give us the same value. Like they contribute the same value in the sum. Why? Because, well, in the exponent there is n squared, so of course that part is taken care of. And negative 1 to the n minus 1 over 2 n, so this part is in both the sums. So this is equal to negative 1 to the power negative n negative 1 by 2 negative n. Okay, so therefore the plus n and minus n contribute the same. So we can just take only the positive odd numbers. So let me just copy this. And okay. Acha, so okay. Yeah. Okay. Now what? Now we define a new function. We define a function theta. And what is theta? Theta is defined as theta of z is equal to sum negative 1 to the power n minus 1 over 2 n e to the pi I n squared z over 4. So we just replaced negative a by iz in this sum and define a new function theta. And this function is defined on the upper half plane, of course. Then let us just write what is theta of x plus iy explicitly, that is, and of course this sum is over positive odd numbers. Negative n minus 1, negative 1 to negative n minus 1 by 2, n e to the minus pi n squared y by 4 times e to the pi I n squared x by 4. Okay. So what is theta of iy? So just this x part is absent, so it's only the y part. And if we use this identity right here, what can we write? We can just replace all the a by y, right? So this is 1 over y to the 3 by 2 sum negative 1 to the n minus 1 by 2 n e to the pi n squared over 4y. Okay. And what is this? This is the same as theta of I by y, like using the definition of theta. It's just, yeah. So this is theta of I over y, and theta of I over y is the same as theta of negative 1 over iy. So now what do we have? We have that theta of negative 1 over iy is the same as y to the minus 3 over 2 theta of iy. No, y over plus 3 over 2 because, yeah. Okay. Now, what we're going to do is that we're going to raise this to the power 8. So, theta of negative 1 over iy to the power 8 is y to the power 12 theta of iy to the power 8. So, if we define delta to be theta to the power 8, then what do we have? We have that delta of negative 1 over z is equal to z to the 12 delta of z in the imaginary axis. Okay. And oh, we did not talk about the convergence of theta, right? What is theta? So theta is this sum right here. And this sum converges absolutely. Because its absolute value is nothing but a sum of n times some Gaussian. So we can bound this by a Gaussian integral. Okay, so theta is absolutely convergent. Yeah. So since theta converges, so theta is a holomorphic function because it's a sum of holomorphic functions, right? Then theta to the 8 is also a holomorphic function. So both the left-hand side and the right-hand side are holomorphic functions. And they agree on the imaginary axis of the upper half plane. Therefore, this is true for all z in the upper half plane. Okay, can someone tell me why this is true? Like which result of complex analysis we are using? This equation holds in the imaginary axis, and both sides are holomorphic. Therefore, like this equation holds everywhere.
It holds on the imaginary axis.
Yeah, imaginary axis of the upper half plane. Imaginary axis of upper half plane. So then we are saying that this equation holds everywhere in the upper half plane.
So it's holomorphic.
Right.
So if it had, if it was not holomorphic, then you have some dependence of the modulus.
Okay.
And then
Well, let's say I define a function f of z that is delta of negative 1 over z minus z to the 12 delta of z. This is a holomorphic. Sorry?
negative imaginary axis, right?
Yeah. But that's not in the domain of our function.
Right.
So, okay. And f is a holomorphic function. If f is a non-constant function, then the zero set of f is discrete. It doesn't have any limit points.
Points?
Limit points. But the zero set of f contains the imaginary line of the upper half plane. So it does contain limit points. Therefore, f cannot be non-constant. F must be a constant function. So therefore, f must be 0.
So can you repeat the argument again?
So if f is non-constant, then the zero set of f is discrete. By discrete, I mean that it does not have any limit points. But
What is the zero set of that?
like all the points in the domain that gets mapped to zero. Okay. But we have seen that the zero set of f contains the imaginary line, which does contain limit points. So therefore, f cannot be a non-constant function. So f must be a constant function. And which constant function it should be? The zero function. I think these details are, we need to go through these details. We need to remember these details. Like to keep in mind that when we can apply those arguments and when we can't. Okay, and you have probably already guessed that this theta to the power 8 is our candidate for the non-vanishing modular form. Okay, so we have verified that delta of -1 over z is equal to z to the k delta z. Okay, we have verified this. Now we need to verify the translation invariance, right? Or not translation invariance, that is periodic function. So yeah. So let's say theta of z plus 1. What is theta of z plus 1? It's sum over positive odd numbers, -1 to the n minus 1 by 2 n e to the I pi n square z plus 1 to the 4. So z to the 4 times e to the I pi n square over 4. Okay. Okay. Now, what is this term? This e to the I pi n square over 4? So n is an odd number, n is a positive odd number. So n squared is what? N squared is 1 mod 8, right? And e to the I pi by 4, it's a 8th root of unity. So therefore, it's also an 8th root of unity. So if we so let's say this number is let's say w. So therefore, theta of z plus 1 is equal to w times theta of z, where w is a w sub 8, let's say. Okay. Yeah, I haven't justified why n square is, so this term is same for all the sums.
So the odd number square is mod
1 mod 8, yeah.
1 mod 8.
Yeah. Okay. So what is this? This is e to the I. So the first term is e to the I pi over 4. Whereas e to the for 3 it's 9, right? 3 square is 9. So it's I pi 9 by 4. And then 25 and so on. So n squared is like 8k plus 1, right? So e to the I pi 8k plus 1 over 4, where k is an integer. So e to the I pi over 4, because the first term is 1. So yeah, this w sub 8 is nothing but e to the I pi over 4. So therefore, theta of z plus 1 is equal to, what is e to the I pi over 4? It's 1 plus I divided by its length, square root of 2 theta of z. So it's e to the I pi over 4. And raising it to the power 8, we get this becomes 1. So delta of z plus 1 is equal to delta of z. Okay. Okay, so we have done everything except we need to verify that delta is bounded as the imaginary part of z goes to infinity. So how do we prove that? Okay, let's consider the sum of theta. So what is theta? Theta is odd n that are positive, negative 1 to the n minus 1 over 2 times n e to the I pi n squared z over 4. Okay, let's write this sum. This sum is what's the first term? The first term is e to the I pi z by 4, right? E to the I pi z by 4. What is the second? Well, I don't think the second terms or the other terms matter, because if we take just theta of z to the power 8, so we get another sum. And that sum starts from e to the I pi 2z. And this is the point at infinity. And we can factor that point up. So, so we have proved that theta to the 8 of I infinity is 0. Because I infinity is well, if we plug in I infinity here, so this term vanishes, right? So of course theta 8 of I infinity is 0. So therefore indeed delta is bounded as z goes to I infinity. So delta is indeed a modular form of weight 12. So looks like we have proved everything except one little thing, that is we need to prove that delta vanishes nowhere. So that's the only part remaining. Also, one very interesting thing, that is the Q expansion of delta. So delta's Q expansion. So delta's Q expansion is essentially this sum, right? And this sum starts from e to the 2 pi I z. So therefore the delta's Q expansion starts from Q. So there's no constant term, and the coefficient of Q is 1, since the coefficient of e to the 2 pi I z is 1 here. Okay. And the other terms don't really matter. Okay, now we just need to prove that delta is not vanishing. For that, it suffices to show that theta is not vanishing, right? So, suppose theta of z naught is 0. So we're trying to get a contradiction. So if it's 0, then without loss of generality, we can say that what we can say without loss, we can say that z naught is in the fundamental domain. Okay, why? Because if theta of z naught is 0, then we can take a SL to the transformation of z naught and still get another point that also becomes 0 under the action of theta. So without loss of generality, we can say that z naught is in the fundamental domain. Okay, now what? So 0 is equal to theta of z naught, and let us write out the sum. That is sum of negative 1 to the power n minus 1 by 2, where n is odd positive numbers, times n times e to the pi I n squared z naught over 4. Z naught over 4. Okay. So let's take out the first term and let's take the first term in the left hand side and take modulus. So then what do we get? We get that the first term is e to the pi I z naught over 4, right? The modulus of it, and is equal to this, right? So there's a sum. Then we use triangle inequality to get this. Of course, odd n that are positive. Which one? Yeah. Yeah, so it should be 3, right? Thank you. And n times e to the pi I n z naught over 4. Okay. N squared, right? Thank you. And we write z naught as x naught plus I y naught. So we get that e to the negative pi I, sorry, there's no I now. Y naught over 4 smaller than sum of odd n that are greater than or equal to 3 n e to the negative pi n square y naught over 4. Okay. Then what do? We divide by this term to get 1 smaller than or equal to sum of odd n that are greater than 3 n e to the minus pi n squared minus 1 y naught over 4. And since z naught is in the upper half plane, we can get a bound for y naught. What is it? So z naught is in the upper half plane. So the imaginary part of z naught is at least what? Okay, 0 is a trivial bound, but it's a bound nonetheless. So, but we need to get a better bound. Square root of 3 by 2, right? Because these 2 points have imaginary parts square root of 3 over 2. Okay, so let me just erase it. Sum odd n greater than 3 n e to the minus pi n squared minus 1 square root of 3 over 8. Okay. And we can write, well, yeah, intuitively speaking, this sum is actually way smaller than 1. So, but we need to prove it rigorously. But we get an intuitive feeling that we are actually trying to prove that this sum is smaller than 1. So let's say n is equal to 2m plus 1, where m is at least 1. So you can rewrite this sum as, well, sum of m being 1 to infinity, 2m plus 1, then
Even greater than 1?
which one?
Even greater than 1 or smaller than 0?
Where? So we're actually trying to prove that this is true. So this sum is smaller than 1.
Sorry, I cannot see it.
So yeah, so this we have so far we have proved that this is true, but we're trying to get a contradiction. So we're trying to prove that this sum is smaller. This is 2m plus 1 e to the negative pi 2m plus 1 whole square minus 1 divided by 4 is m square plus m, square root of 3 over 2. Okay, and since m is positive, so m square plus m is what? At least 2m, right? So this is smaller than or equal to sum over m 1 to infinity 2m plus 1 e to the negative pi m square root of 3. So this is the power series in e to the negative pi square root of 3. So let's write the function of this power series. Let's say 2m plus 1 x to the m. And if we expand this power series, we get that this is 2 sum of mxm plus sum of x to the m. And this is 2x by 1 minus x squared and x over 1 minus x. Because the sums are starting from 1. Okay. And the value we have here, this is f of e to the minus pi square root of 3. Okay. And well, you can easily show that this f function is increasing in 0, 1, in the interval 0, 1. And also, and why is this true? Because the derivative of f is positive here. Okay. And also you can also show that the value where f becomes 1 is actually, let me just write it. So 5 minus square root of 7 over 4. Okay, it's just solving a quadratic equation. So, yeah. And this is like approximately 0.218, where e to the negative pi square root of 3, this is approximately 0.0043. Since the function is increasing, so we can say that f of e to the negative pi square root of 3 is smaller than 1. So therefore, this sum is smaller than 1, and so we get a contradiction because we have that 1 smaller than or equal to the sum, which we just proved that is smaller than 1. So we get a contradiction. So no such point exists where theta vanishes. So yeah, we're done. Oh, I guess we can take a quick 5-minute break now. Now we're going to prove the long-awaited dimensional formula. So that is the dimension of mk, the vector space of all the modular forms of weight k, is given by floor of k over 12 if k is 2 mod 12, and floor of k over 12 plus 1 otherwise. So if k is not 2 in mod 12. Okay. So we are going to prove it by induction, and for that, first we are going to prove it for k equals to 0, 2, 4, 6, 8, 10. Then we are going to induct upon these base cases. Okay, so what if k is 0? If k is 0, then according to our formula, the dimension should be 1, right? Okay, let's see if that is true. So if k is 0, then what? Then let's say I take f from the space of modular forms. Yeah. Then suppose the constant term in the Q expansion is a naught. So a naught is f of I infinity. Okay. Then what we can do is that we can take this quantity f of z minus a naught divided by delta, where delta is the weight 12 modular form that vanishes nowhere. Okay. So now, yeah. So my claim is that this is the modular form of weight negative 12. So why is that? Well, like, do we see that it clearly satisfies the modularity conditions? Because the numerator satisfies the modularity condition for weight 0, and the denominator satisfies the modularity condition for k equals 12. So therefore, the quotient satisfies the modularity condition for 0 minus 12 weight. So that is negative 12 weight. So the modularity condition is taken care of. So the only thing remaining is the boundedness as we go to I infinity. Okay. So yeah. So for that purpose, let's notice that this has a simple zero at I infinity, right? And this has a zero of positive order, of order at least 1, right, at I infinity. Because f of I infinity is a0. So this is 0. So therefore the quotient is either 0 or it's a finite number. Because the order of 0 of the denominator is smaller, like smaller than or equal than the order of 0 of the numerator. Therefore the quotient therefore the quotient is either 0 or a finite number. So the main point is that the quotient is bounded, right? Bounded at I infinity. Okay, so therefore this is a modular form of weight negative 12. But we know that the only modular forms of negative weight are 0. Therefore, f of z minus a0 over delta z, this must be 0. So f is the constant function a naught. Okay, so we have proved that for k being 0, the only modular forms are constant functions. That's actually a very interesting point, because what are the modular forms of weight 0? That are like f of az plus b over cz plus d equals to f of z. There are holomorphic functions that are SL2Z invariant, and that are bounded as we go to infinity. Okay, so we have actually proved that the only SL2Z invariant functions that have the nice bounded property are the constant functions. So this is a very interesting result in complex analysis. Okay, so we are done for case k equals to 0. And we can essentially do the same reasoning for k being 4, 6, 8, and 10. So let's do it real quick. If k is, say, 4 or 6 or 8 or 10, then again let's take a modular form of weight k, and suppose a0 is f of I infinity. What do? We just do that we define a new function f of z minus a0 divided by delta z. But this time, instead of taking just a0, we take this. Well, because what is the q expansion of ek? The q expansion of ek is 1 plus like something like this, right? So ek at I infinity is 1. And using a similar reasoning as before, all these functions, they satisfy modularity condition for weight k minus 12. Because the numerator satisfies modularity condition for k, the denominator for 12, therefore m sub k minus 12. And also using a similar reasoning, the denominator has a 0 of order 1, and the numerator also has a 0 of order at least 1, of course. So therefore the quotient is bounded. So it's a modular form of weight k minus 12. So therefore, again, using a similar reasoning for k being 4, 6, 8, and 10, all these numbers are negative. So f of z must be a constant multiple of ek. So we are also done with the 4, 6, 8, 10 case. Now we just have to prove the k equals to 2 case. So if we look at the formula, what should be the value of the dimension of m sub 2? 0. Okay, let's try to prove it. Suppose we take a modular form of weight 2. So we need to show that this modular form is a constant zero function. Okay. So now what we are going to do is that we take f squared. And my claim is that f squared is a modular form of weight 4. Can you see why? If f is a modular form of weight 2, then f squared is a modular form of weight 4. In fact, another result is true. That is, if f is the modular form of weight k and g is the modular form of weight l, then fg is the modular form of weight k plus l. Okay. Right. And using the modularity conditions, you get that f of negative 1 over z is equal to z square f of z. If we plug in z equals to I, what do we get? F of negative 1 over I is I. It's minus 1 f of I. So f of I should be 0. But then, also since f square is a modular form of weight 4, and we know that the modular forms of weight 4 are nothing but a constant multiple of E4, right? So f square is just c times E4. So therefore, c times E4 of I is 0. And what is E4 of I? E4 of I is, let's write the Q expansion 1 plus 240 sum of sigma k minus 1 of n q to the n. What is the value of q for I? Like q is e to the 2 pi I z, right? If we plug in z equals to I, we get that e to the negative 2 pi. So there is e to the negative 2 pi n. Okay. Is this ever 0? Of course not. Because these coefficients, sigma 3, these are positive numbers. And so are these, e to the negative 2 pi n. So therefore, the only case remaining is that, so c must be 0. So if c is 0, then obviously f square is 0, so f is 0. So dimension of m2 is 0. Just m2 is just the constant zero function. Okay, so we are all done with our base cases. So we have verified the dimensional formula for k smaller than or equal to 10. Okay, now essentially we are going to do the same things like what we have done so far. So what we are going to do is that now take k at least 12. Okay. Then again take a modular form of weight k. Take a0 to be f of I infinity. And again f minus a0 ek over delta. This is the modular form of weight k minus 12. Using the same reasonings. Okay, now what? So therefore, f minus a0 over ek times ek is equal to delta times g, where for some g in m k minus 12. So we can form a linear map. That linear map is from the direct sum of c and m k minus 12 to mk. What does this map do? This map takes a complex number c, a modular form of weight k minus 12, and map it to maps it to c e k plus delta g. And this map is a surjective function. Why? Because we have just shown that given any modular form of weight k, we can find a0 and g such that f is equal to a0 ek plus delta g. Okay, so this map is surjective, and is it injective linear map? Is it injective? The answer is yes. Why? Let's say we take some c comma g from the kernel of this map. Let's call this map phi, kernel of phi. Then what we have is that c ek plus delta g is 0. Now let us compare the constant terms of the Q expansions. The constant term of delta is 0. The constant term of ek is 1. So therefore, C must be 0. Since C is the constant term of the Q expansion of the left hand side. So C must be 0. So if C is 0, then delta G is also 0. And we know that delta is non-vanishing on the upper half plane. Therefore, G is 0 on the upper half plane. So we get that only the zeros are in the kernel. So therefore, this phi is injective as well. So this phi is an isomorphism of vector spaces. Therefore, the dimension of mk is the same as the dimension of the direct sum of c and mk minus 12. And this is dimension of this is dimension of c plus dimension of mk minus 12. Dimension of c is 1, and so by induction we are done. So we just proved the base cases for k equals to 0, 2, 4, 6, 8, and 10. And for the higher ones, we can just reduce by 12 every time. For instance, if I have to find the dimension of m, let's say 200, that is nothing but 1 plus dimension of m. What is 200 minus 12? It's 188, right? So we can reduce 12 every time and add 1 here. So after some time it becomes 200 divided by 12, the floor of it minus 1 plus dimension of 200 mod 12. Right? And we know what this is. From the from the base cases we know what this is. And yeah, so finally we have proved that the modular forms are finite dimensional, and the dimension formula is, again, I love to write this dimension formula. It's so beautiful. If k is 2 mod 12, and k over 12 plus 1 if k is not 2 in mod 12. So yeah, so this is a very, very nice formula. And of course there are some consequences. The first consequence is that, well, E8 is a modular form of weight 8, so is E4 squared, right? And the modular forms of weight 8 forms a vector space of dimension 1. So these two are just a constant factor apart. But if we compare the constant term in the Q expansion, the constant term of the Q expansion of E8 is 1, and the constant term for this one is C. So therefore C is 1. So finally we have proved that E8 is E4 squared. And also this has a very nice consequence as well, because we know that like EK is 1 plus 240 sum of sigma k minus 1 n q n. Sorry, not 240. 240 is for specific n. It's 2k over bk. And if we compare the coefficients of E8 and E4, we get a very nice identity, that is sigma 7 of n is equal to sigma 3 of n plus 120 sum of sigma 3m, sigma 3m minus 1. Sorry, n minus m. Sorry, n minus m, where m runs from 1 to n minus 1. M is from 1 to n minus 1. So this is a very nice identity from number theory that we just proved using modular forms. Okay, also, yeah, that M12 is a vector space of dimension 2, right? So it has a basis that has 2 elements. And we know that E4 cubed is a modular form of weight 12. So is E6 squared. And these two are linearly independent. Why? Let us just say why. Well, I think I did not write what these two, but I did not like expanded these two. So let me just copy this from my notes. Yeah. So E4 cubed is 1 plus 720Q plus something, and E6 squared is 1 minus 1008Q plus something. So clearly these two are not linearly independent. So therefore, M sub 12 is spanned by these two modular forms. Okay. And also, another very interesting fact. So suppose F is a modular form of weight K. And also suppose F is non-vanishing on the whole upper half plane. Well, then we have seen that K must be a K must be a multiple of 12. Because if 3 does not divide K, then F of a cubic root of unity is 0. And if 4 does not divide K, then F of I is 0. So therefore, K must be divisible by 12. Okay. Uh, uh, uh. So then f has to be delta to the power k over 12 times a constant factor. So all the modular forms that are non-vanishing everywhere are only uh, the if the constant multiples of exponents of the modular form delta. Okay, so this is an exercise for everyone to prove that this is true. All right, yeah. Should we prove the Eisenstein basis today? Yeah, I think we can do it in like real quick, 10 minutes. Okay. So, yeah, Eisenstein basis. What is Eisenstein basis? Uh, it says that let's form this set E4 to the A, E6 to the B, where A and B are non-negative numbers. Also 4A plus 6B is K. So this is a basis for MK. That is, all the modular forms of weight K are just linear combinations of these modular forms. Okay. The proof is actually really simple. So suppose I'm introducing a new number, n sub k. So n sub k is the number of solution of a specific Diophantine equation. Number of solutions of the Diophantine equation 4x plus 6y equals to k, where x and y are positive. Okay, can someone tell me how many solutions are there for 4x plus 6y equals to 12? If I further impose that x and y are both non-negative. So in general, such a linear Diophantine equation has infinitely many solutions in integers. But true. There is 4 times 3 plus 6 times 0, and the other is 4 times 0 plus 6 times 2. Okay. All right. Now, yeah. Okay. Suppose I have 4x plus 6y equals to k. Then, let's say, 4x prime plus 6y prime equals to, let's say, k minus 12. So this equation has n sub k minus 12 solutions. And to each of the solutions, I can add this one and this one. Right? Sorry, no. No, it gives twice, but it should not be twice. So I'm trying to show that n sub k is equal to 1 plus n sub k minus 12. So that is the number of solutions of this Diophantine equation has this recursion. Let's see. Yeah, that is the idea. So, but I don't have a solid argument for it, like why this is true. Yeah, I'm getting an intuitive feel. Of course, this is true. Hmm. 4x plus 6y is, if that's 12.
So what was the geometric reason why 4x plus 6y equals to 12 as only two solutions?
Geometrically, yeah, it's a line,
X and y are positive.
right?
So how can we
Sorry, it's this line, right? And we are saying like which lattice points of the first quadrant it goes through. It goes through only these two lattice points.
So those are the solutions.
Yeah.
And,
And as we increase the value of k, so this line gets shifted.
right, so more and more points.
Yeah.
Yeah.
But my claim is that like as we increase k by 12, we get only one more solutions than the previous one.
Right.
In k plus 2. So let's take a solution from here. 4x plus 6y equals to k. And yeah, and suppose k is at least 12. Okay. Then yeah, both x and y, like at least one of these equations should be true. At least either x greater than 3 or y greater than 2. So if none of these happen, then x is smaller than or equal to 2, then yeah, then k must be smaller than or equal to 10. So one of these must be true. Okay, then what happens? Then what happens is that suppose this is true. If this is true, we can take 4x minus 3 plus 6y. This is a solution of what? This is a solution of k minus 12 plus 12. If this is true, then what we can do is that we can keep 4x the same and 6y minus 2 plus 12. This is a solution of k minus 12. But we are overcounting. So of course, like both of these can be true simultaneously. So that's the case I'm trying to figure out. Six times y minus 2 plus 24. Okay, so yeah. So therefore, n sub k is equal to what? Is equal to n sub k minus 12 times 2 minus the solutions of this, minus n sub k k minus 24, right? Times the number of solutions of this equation. Number of solutions for 24. What is the number of solutions for 24? It's 12. For 12, it's 2. Is it 3? Uh, 3, 3, 2, 6, 0, and 0, 4. Yeah, 3. Or then we can basically apply induction on this equation, because we know the value for nk for k being smaller than or equal to 10, right? So furthermore, we need to just calculate the values for k being 12 to 24. Then we can just plug in these values, and yeah, inductively we can prove it. So inductively we can prove that n sub k plus 12 is basically 1 plus n sub k. Okay. Yeah. So n sub k is equal to 1 plus n sub k minus 12. Okay, if this is true, and also n sub k is equal to dimension of mk for k being 0 to 10, right? We can easily verify this. So therefore, n sub k is equal to dimension of mk for all k. So the set we have picked E4A, E6B, where 4A plus 6B equals to K, and A and B both are positive. The coordinate of this set is equal to the dimension of MK. So this set is of the right size, so we just need to show that all these terms are linearly dependent. So let's try to prove it. So say sum of CAB, E4A, E6B is 0. Okay. Now, if there is a term with only E4, let's say if the term C, let's say K over 4, comma 0, let's put a comma here. E4 to the K. So if there is a term like this, then what we can do is that we can evaluate this thing at I. What is the idea behind this? The idea is that E6 of I is 0. Well, we did not prove it, but we mentioned that if k does not divide 4, then if we take a f from mk, then f of I must be 0. So using this idea. Okay, E6. Yeah, sorry, 4 does not divide k. Thank you. So using this idea, if we evaluate it at I, then, and E4 of I is non-zero. We've seen this actually during the proof that the dimension of M2 is 0. Right? During the course of that proof, we took a modular form of weight 2, squared it, and then the f squared is a constant multiple of E4. Right? Then we evaluated it at I. Okay, so E4 of I is non-zero. Therefore, this term must be 0. So, yeah. So we get that sum of CAB, E4A, E6B equals to 0, where A is at least 1, B is at least 0, and A 4A plus 6B is what? K. So you can factor out E6. You can factor out one copy of E6 right here. So sum of CAB, E4A, E6B minus 1, E6 is 0. Oh, right. Yeah. It did. Yeah. So, yeah, we have shown that the terms with b equals to 0 has coefficient 0. Yeah, so like this. Yeah, thank you. So you can factor out E6 and get a new equation, this. And again, what we do is induction. So this is the linear independence condition for k minus 6. So, and yeah. And so what do we need to do? We just need to verify the linear independence for k being smaller than 12, which you already did. So we are done. So therefore, this set is a basis. So yeah. Does anyone have any question? Yeah, this is indeed a very nice result. This is one of my favorite results from all of math.
Is okay with the
No, not this. The Eisenstein basis. Yeah. So yeah, next time I guess we'll see some cool applications of these facts. Yeah. So using these tricks from modular forms, we can actually prove that the zeta function, like the good old zeta function we all know, zeta of k is a rational multiple of pi to the k.
And then it's zero is like imaginary axis.
Well, yeah, of course, yeah. We'll try to prove the Riemann hypothesis as well.